So when you go into the laboratory, it'd be nice to have things like temperature, pressure, and volume, and hold those constant and have some function that you could calculate to see whether it'll be spontaneous. So what we're going to do is define two new energy terms, free energy terms we're called. It's A is U, internal energy, minus Ts, and we'll define that's the Helmholtz free energy. We'll define the Gibbs free energy as the enthalpy minus TdS. It's called free energy because essentially what you're doing is subtracting off this Ts term, which is like wasted energy, energy that goes to heat and not available to do work. So this free refers to energy that's free to do work. We'll find this at constant temperature and constant pressure and temperature here. Looks like there's a slight mistake. Let me check that. At temperature and volume. That's right, that'd be volume. All right, so let's see what this definition gets us in terms of criterion for spontaneity. All right, so we're defining A. We're going to define that as, well, let me start this on a new page so we can be more precise. So A is defined as the internal energy, U minus Ts. We're subtracting off this unuseful energy entropy. dA is equal to du minus TdS minus SdT. Nothing new there. Let's solve this for, say, du. du will be equal to dA plus TdS plus SdT. And we know that du is less than TdS minus PdV. And again, just remember we're only doing PV work. That also was the case here. When we went down here, only PV work. That's one of the assumptions we've made there. Let's take this term, put it over there, take that term, put it over there. So we have dA plus TdS minus SdT. Ooh, that's kind of neat. Plus SdT, blah, minus TdS plus PdV has to be less than 0. We take those things, that is 0 less than 0. And look at the TdS terms cancel out. Ooh, so we got rid of entropy. So dA plus SdT plus PdV has to be less than 0, or dA at constant temperature and volume has to be less than 0 for spontaneous process. So if you want something that's occurring at constant temperature and volume, and you want to see whether it actually occurs, goes forward in time, calculate the Helmholtz free energy and see whether that is less than 0. If the Helmholtz free energy decreases with this process, then the process will occur spontaneously. Just touch base here. So there we go, temperature, volume. And finally we get to this Gibbs free energy, given the symbol G, which you probably are familiar with from introductory chemistry and other courses, other science courses. So let's just see where that comes from. G we're going to define as H minus Ts. So we're going to sort of subtract off some non-useful energy. S as units of joule or of energy per Kelvin, and you multiply it by Kelvin. So this is energy. Ts is energy, and you're going to subtract off from the enthalpy that energy, and we'll see what happens. H is U plus PV minus Ts. So dG will be du plus PdV plus VdP minus TdS minus SdT. And we're going to do the exact same we did for the other three cases. We're going to substitute in, we're going to solve this for du. du is dG minus PdV minus VdP plus TdS plus SdT. And we're saying from the combined first and second laws that is less than TdS minus a PdV. And again, only PV work. So let's take this term, put it over there, take that term, put it over there. So here we have dG minus PdV minus VdP plus SdT. We're taking this over minus TdS plus PdV. and that has to be less than 0. And let's see what cancels out. TdS cancels out. There goes the entropy. A PdV cancels out. So there goes the volume. And so we're left with dG minus VdP plus SdT has to be less than 0. Or dG at constant P and T, pressure and temperature, has to be less than 0 for spontaneous process. So finally we get something useful for the chemist. If you have like a chemical reaction occurring at constant pressure and constant temperature, and you want to know whether the reaction will spontaneously go from the reactants to the products, you calculate the free energy change. If the free energy change drops or is negative, in other words, the free energy drops, becomes low, then the reaction is spontaneous. So remember at the very beginning, or maybe even from introductory chemistry, if we look at, say, the free energy versus time, we have this graph, and we have here reactants. Well, let's make this the progress of the reaction. Okay, it goes like this. It's down here. It goes like this. What you want, and this says is constant pressure and temperature, so it's just sitting in the laboratory in a beaker that you maintain a constant pressure. This is spontaneous. dG is less than 0. You're decreasing the free energy. And this way is spontaneous. And right here, it's not spontaneous. It's not going that way. You already reached a minimum, so that's the equilibrium point. So in both cases, you want to decrease free energy for a spontaneous process at constant pressure and temperature. Finally, something we could use. All right, so that's it for spontaneity for now, and in the next lecture we'll consider some other concepts. In particular, we'll get heavy into partial differentials and variables and so on, and we'll be able to derive some interesting relations between these quantities. So just to review, what do we have? We have U, H, A, and G. So those are the four thermodynamic functions. We have U, we have H, we have A, and we have G. U is the internal energy, H is the enthalpy, A is the Helmholtz free energy, and G is the Gibbs free energy. This is useful for constant temperature and pressure. This is useful for constant temperature and volume. And this is useful for constant entropy and pressure. And this is for constant entropy and volume. So really these are the two that we have easy experimental access to these constant parameters. All right, so just remember that, and I think we'll be okay to go on. Thanks for listening.